Okay, so this is a string, right? I think this is a example for the Fourier sine. So you have a string from 0 to L and found the amplitude. So the string satisfies the differential equation. Yeah, we are our different from the textbook. We haven't talked about partial differential equation, but this is just like a preview of you can solve different partial differential equation using different method, and some method using Fourier series, some using Fourier transform. I think hopefully we can get the Fourier transform an example similar to this. This is a wave equation. So, but just for now, you just consider this is a partial differential equation depends on partial derivative. I think we talk about partial derivative a little when we do the complex analysis. So, but whatever. Now you just try to solve it. This is a domain from 0 to L and subject to the boundary condition. We have 1x 0. This is the initial condition t at t equals 0 is 0. And then another initial condition is the derivative. This is like a velocity. This is also 0 at t equals 0. Or you can say it's t and then set t equals 0 because you take the derivative first and set to 0. That is a, like the other function, right? And then I think there should be a boundary condition claimed at both ends. So the boundary condition is y0 y l d. That's what it means by the first sentence. It's fixed. The value is fixed. Okay. Now try to find the solution. Write down the solution. The answer is given. So the first thing you can you do is write down the form of the solution using Fourier series that satisfy this two boundary condition. And we talk about that in class. That it's easiest for a finite domain. You can use all three kind of Fourier series. You can use a full Fourier series or Fourier cosine series, Fourier sine series, and you choose which one to use to most convenient for your problem. And for us, because you fix the two boundary, so it's easiest to use the sine series. In that case, you can write this formally. The sum over all the mode. The sine series start with 1, and you have some coefficient. So for the names is C sub n to I think using a more consistent is B sub n in the text is B sub n. And sine to satisfy both the boundary conditions and pi x over L because when x is 0, obviously it satisfies this is sine 0 is 0, and for x equals L, this divided by L to be n pi, sine n pi is always 0 also to satisfy the second boundary condition. So this will satisfy the boundary condition, and it's a complete expansion because Fourier sine series is complete. So this is the general form. Now the the rest is to figure out what the b sub n is, and to figure that out, we use the the equation of obviously use the equation the and the initial condition, right? So at at I mean you can see which one you want to apply first. Let's try the equation first, right? And so with that, partial square y partial x square. Obviously, just take the area of that one. And so you pull out the factor minus n square pi square l square, right? And still sine b sub n t sine. Okay, and that equals the right hand side, and so you need that equals to 1 over v square, and partial square partial t square only operate on b sub n. So that means now this is a total derivative is not a positive b square b sub n, and the same sign function. Okay, so now you have an equation for all the b sub n because the coefficient individually has to be equal because these are a complete expansion. So the coefficient is unique. So therefore, this equals to that means the coefficient has to be the same. So this means b square b sub n b square equals to multiply v square over there minus n square pi square v square over l square times b sub n. There's a b sub n. And now so this process reduce the partial differential equation to a ordinary differential equation. This is not just one equation. This is for all. You know that this, you already have the n is from 1 to infinity, so you have a infinite many ODE, but that is nothing because you know how to solve this. Do you know how to solve this? Hopefully, yeah, some of you learn about that. This is just a simple harmonic oscillator equation. So, solution can be written in sine or cosine. It doesn't matter, or exponential function. If you stay with all the real, because this is real, stay with the real expression. So you write it like so. This implied. Let me write. It's getting too low. So the solution is b sub n would be now if you introduce some variable. How do you say? C sub n 1 like cosine. The square root of this factor will give you n pi v over l times t. Then the second term, c sub n2 n pi v over t. V over l times t. Okay, so these two are the two independent solutions or the simple harmonic oscillator, right? You all know that. Okay, and so this satisfies this differential equation. So now you reduce the task to just solve for all the c sub n, c sub n1 or c sub n2. Okay, now you use the initial conditions. There are two initial conditions, this one and that one. So y at t equals 0 is 0. So it means that going back to here, b0 is the whole thing is 0 by the Fourier series. You know that all the coefficients must be 0 because again this is a complete expansion. So uh, so it means the first condition means that b sub n 0 is 0. So we substitute 0 in this one. So we get this is put 0 here. This term is 0. This term is just 1. So c sub n1 equals to 0. So you don't have this term. You only have the second. Okay. So now we do it just to solve a c sub n2. So now you use the derivative initial condition. So if you just take the derivative and get to b sub n. So basically, or the other way around is you can say you can use the delta function. I think the textbook suggests you could use that use the completeness condition that I think is in the previous problems 19.2.17a, which give you the completeness condition that is the x minus a is. I mean, we talked about that in class. You can rederive that easily by just substitute the Fourier series to the equation. It's not difficult to rederive. The problem is whether it's useful for this problem. Okay, without the completeness condition, so you put it back to here. It means no, there's a summation. I forgot. Sum over n of 1. Okay, that looks like this. Like it. Okay, so put it back this to here. So partial y partial t at 0 is so you put this here. You get the 2. Where do you have a v sub 0? Is this v sub 0? I mean, just figure out what the v sub 0 is. This the same v? The equation is that v. This is called v sub 0. The answer only depends on v sub 0, not v. Well, yeah, well, there's a v sub 0 divided by v. Okay, so the two might be different. Okay, so whatever. So cancel just the L. You have 2 v sub 0 sum over n. Okay, now you use this and take the derivative of that one. I mean, take the ddt of this one, which is db dt, and db we already figured out is this one without the c sub n1 is 0, and only have that term, and take the time derivative of that one. That give you that is sum over 1 to infinity, and this is, I mean, you can take the time derivative of that one, give you minus n by v over L cosine by v over L. That's p sub n, the derivative dp sub n dt is this one. And then we multiply by sine. Okay. And now you recognize these two over infinite series of sine, the basis of sine function. So they are complete. So these two has to be the same. I mean, this haven't set to 0. You need to set to 0. In all the cosine term becomes 1. Put 0 here, all these are 1. Oh yeah, I forgot the C sub n2. No, because you need to figure out what the C sub n2. Okay, so this times this equals to 2 v sub 0. So this means that C sub n2 equals to, there's a minus sign.
Differential of sine is.
Say that again.
Differential of sine theta is cos theta, not now.
Oh yeah. The division has a plus. Okay, thank you. Okay. See, n2 is 2 v sub 0 times L divided by n by 3. Okay, now that's the last test we need. You substitute this back to here, you get all the b sub n. Putting b sub n back to here, you get the solution. So now you can write down the solution. Xt is b sub n has this coefficient for the c sub n. So you put everything independent of n out to v sub 0 L pi, no n, just pi v sum infinity and 1 over n sine n pi v t over L. This one going to here, and then this one. Can you see that? It's too low. Everyone can see that, right? So this should be the answer. We should see it. Why he has that? Oh yeah, I forgot it. There's a sine n pi. There's a sine n pi. Still copying wrong. But that's missing one term. So this one is going over here. Okay, missing one term. 1 n pi a over n. N pi n pi vt over L. Okay, so this is the correct. Okay.